Okay, so what is a neural network and why should we care about them? Well, today I will show you what is the easiest way to think about one, how to use them, what basic math concepts you need to know to get into machine learning, and what things I consider to be overrated for a beginner. So let's start. Imagine that we have a robot that we want to teach to recognize cats and dogs. We also have an infinite amount of images, all of them labeled this is a cat, this is a dog. We upload all of these images to our robot body and we just managed to build a perfect model that can tell us if an image is a cat or a dog. No matter how many images we throw at it, it will always be right. Now here's the kicker. This does not work in the real world. First of all, we cannot really store an infinite amount of images, like the robot will run out of memory, and we also don't have all the possible images of cats and dogs. We don't really know how dogs or cats for that matter will look like in the future. Luckily for us, we have a solution, and that is neural networks. These things are a way to approximate that perfect model that we imagined. So you can think of them as a black box that take an input and give you an output, just like the math functions you learned in school. There are many problems that can be solved with neural networks. For today I want to focus on a simple one, recognizing cats and dogs, also known as a classification problem. I will build everything from scratch, so I encourage you to check out the description for the code. Let's start with the simplest neural network, the perceptron. So the perceptron is something like, you can imagine it like a single neuron, and it has an input, right? In our case, let's imagine it has a single input x, and it has a weight and also bias, right? And it gives us an output, which usually it's called like y or z. Let's call it z in our case. And the function for the perceptron usually looks something like f of x is equal to w times x plus b. And here w represents the weight, b represents the bias, and you can think of these two numbers as the parameters of the function or of the model. The perceptron is a linear function because it is a straight line, so if we would input some numbers for w and b, the graph for that function will probably look something like this, right? So this would be x and the y-axis, and our function will look something like this. So it's a straight line. That's why it's like a linear layer usually in machine learning. Now, as I said, we can give some input to this function, and if you think of the input as our image, things become a bit more complicated. How can we take an image and, let's say it's a cat. I don't know how to draw a cat. We have an image and we want to multiply it with weight, but how can we do that? It doesn't really make sense to multiply a number with an image. Well, the easiest way to achieve that is to actually take our image and flatten it into a list of pixel values. So instead of an entire image, we would have only numbers, one number for each pixel. Or usually, since it's RGB image, sometimes it also has alpha, but in our case we'll have just RGB image. We are gonna have values for each pixel in like RGB. So now it makes more sense, right? We know how to multiply like a number with an array of numbers. Let's imagine that it's 0, 5, 0 0.1, and so on, like another 0 0.1. We know how to multiply like a number with a vector or a list of numbers. That's pretty easy. So actually our function will turn into something else now. It's gonna be fx, and it's gonna be x1, x2, and so on, like xn. And these are all the pixel values that we have, right? So it's gonna be w times x1 plus w times x2 and so on. At the end it's gonna be still plus b. B doesn't change, it's still a number. But this thing doesn't always work. Like in some cases, sure, it might be like enough to have a single w, but usually in machine learning we have one w for each input, so it's gonna be w1, w2, and so on. So it's not that we have a single number, we actually have also another like w is gonna be w1, w2, and so on. until wn. But now comes another problem. How do we multiply two vectors, right? So, I mean, we just saw how that output should look like, and if you have a bit of, like, let's say algebra knowledge, you recognize this thing as a dot product. So in the end, our fx function, it's still gonna be w times x plus b, but instead of multiplication here it's dot product, so that's the only difference. But you know, you don't have to be scared about like more complicated uh, math operations like dot product. This is just a way to, you know, have some easier way of writing this entire multiplication from here. It's like a shortcut of writing that, so it's not that complicated after all. But yeah, we can see that the formula is still the same as the original one, so there's not gonna be that big of a difference. And now your question might be, okay, but how can we use this perceptron to recognize if we have a cat or a dog in an image? Well, we can think of the output, so z would be the output, as the score of that image. So here we have you know, x1, x2 and so on. We pass it through the perceptron and we get back a score. So you know, this score is gonna be, we would like it to be between 0 and 1, right? Between 0 and 1, and this number will represent the probability of having a cat in the image, for example, or a dog. Depends how you want to interpret it. And if the score is closer to 1, then we have a cat, and if the score is closer to 0, then we have, you know, I didn't draw a dog, but you can imagine that we would have a dog in the image. And this kind of problem is usually called a binary classification problem, and it's a binary classification because we have only two classes. If we would have multiple classes, then the problem would become a bit more complicated, but we'll touch on that later. I think as a starting point, binary classification is the best way to start because we only require like a single perceptron. We don't require anything else. So, you know, that should be the easiest way to start. Now that we have a really simple neural network, so the most basic one, right, with weight and bias, a single weight and a bias, and with some inputs, so these would represent like x1, x2, x3, and so on, we get some output out of it, right? So y, or as I called it earlier, z, this is the output of our neural network. Now we would like to know how well it's doing, right? Because, well, it's not the perfect one that we talked about earlier, so clearly it's gonna have an error. So we want to see how close this z value is to the real one. So let's imagine that we have some input values, and associated with them we must have like the real label, which, I mean, in machine learning people usually put like a, I don't even know how this one is called, but like a symbol on top of the letter to represent like the true value. So yeah, let's imagine that we have an x, and we also know the true value for that x, like the true label. In our example, we have an image and we know already if it's a cat or a dog. So, you know, this might seem counterintuitive, but like we already know it's a cat or a dog. Like, why do we need the model then? Well, you know, maybe we have an image that we don't know what it's inside. Let's call it x1. So maybe for this one, or x, I don't know, let's call it x, and we put, I don't know, like, let's say we have an image that we don't know what it's about, and we don't really have the possibility to look at it to decide for ourselves, so we need to use the model for that. So then it makes sense to first test the model and see how good it is, so that we know if we can trust the prediction or not. So in this case, we pass the original image, which we know the label of, through the model. We get back a z value, and we also have the true value. Now, sure, this thing, as I said earlier, is a probability, so it's a probability, it's not really the label. And this one you know, it's going to be a 0 or a 1 basically, so it's still a probability if you think about it. So the cost that we can use for this kind of functions, you know, if we want to keep it simple, should be something like the difference, right? So z minus this. So this would be our initial cost. Like this is the easiest way to compute it. Like what's the difference between the two? But now thing is that I guess a simpler way to do it, like I don't know if it's a simpler way to understand it, but we might as well just say that we square the difference because we are more interested in how big the difference is, not really the sign. So if you think about it, if we have 0 minus 1, this would be minus 1, 1 minus 0 is 1, and you know 1 minus 1 is 0, so it doesn't matter, it's perfect. But we can also have 0.5 minus 1, which is minus 0.5. So as I said, we are not that interested in the sign, but we are more interested in the value itself. So the 1, the 0.5 and so on. So now you might say, okay, but why not just use the absolute value, right? So why not just do this thing? You cannot compute the derivative of this or something like that. You just have to trust me that this is the better way. Like, who cares about the absolute value? We can just raise it like to the power of 2, square it, and we get and like this way we get the mean squared error. That's how it's called. So MSE, or like we get the mean squared error. And yeah, if you want to know more about it, you know, mainly I guess the reasoning behind using it is that it's differentiable, so you can compute the derivative easily for it compared to the absolute value. So you know, that's the main reason we have to use it. So no, you can trust me on that, but this would be the way to compute the cost. So we take the prediction, we subtract the value that we got, and we raise it to the power of 2. So pretty self-explanatory. So we would get the error of our model. And now if the error is pretty small, we would know that we can trust the prediction on a new X thing. But if the error is pretty big, then we cannot really trust the prediction. So, you know, it is what it is. Train the model more, gather more data, do stuff like that until you are sure that the predictions are gonna be good. So for our simple problem of doing a prediction between, you know, cats and dogs, the perceptron is enough as a, you know, neural network. But the issue with it is that it can output any number. So if you can think about it, let's say that we have a weight W is 100 and bias is 1000 or something like that. Like if you output a number, like any number, you know, you'll get something like, let's imagine that we input 1. So it's going to be 1 times 100 plus 1000. It's kind of not really looking like a probability. It's pretty weird, right? So a good way of you know, making sure that our output is going to be between 0 and 1, because that's what we want for probabilities, is to use an activation function. And this is why I used z and not y, because people usually have z, and then after you apply the activation function you get y back. But yeah, what's the activation function? Well, not really that important how it looks like. Like we are gonna use sigmoid. It's I think it's like this symbol, and it's called sigmoid, right? And the purpose of this function is to take any number that we have, so we can have any number, and it's gonna turn it from like, is it called R, to 0 1 or something, right? So this is how the output of the function is going to be. Like it takes in any number and it gives us a number between 0 and 1, and pretty much that's the most important idea of this. Like you don't really have to understand like why it works or how it looks like, although you know I can show that it's if you input x, it's gonna be 1 over 1 plus e to the power of negative x. So this is how it looks like. And I mean, I have no idea who managed to think about it, like what the actual fuck, how can you think about something like this? But if we plot this thing, it's gonna look something like this. So this is the y-x, and this is like, I don't know, like -2, and this is like, actually I fucked it, but it should come through the middle, but I cannot draw. And yeah, so when it comes to almost 2 or -2, it almost becomes like, here it's 1 and here it's 0, obviously. But yeah, like if you think about it, it's going to be between 0 and 1 always, so that's pretty cool. So how can we use this function? Well, we can say at the end here, after we computed z, that y is going to be sigmoid of z. So we add here an extra step. I mean, I have to delete this. We add an extra step of sigmoid and we get y out of it. So now we actually have the probability that I promised. So yeah, that's the reason of using activation functions. You want to make sure that the output is in a certain range of values, because you cannot really force the neural network to, I mean, you can force it by training, but it's easier to use the activation function, so that's the reason for it. Now that we have the basic idea of a model, let's try to actually load some data and write some code for the implementation of the neural network. Alright, so let's try and use the dogs versus cats dataset from Kaggle for our example. And this one contains like 25,000 images. All the images are not really, let's say, properly resized, but we'll try to do that ourselves. Yeah, basically I'll be using stb image for that, for being able to load images and write them. And I want to use C just to show how to do everything step by step, because if we use PyTorch, it's gonna be like 3 lines of code. It's not really that interesting, but I want to see like each step, how it's implemented, because it's gonna be more useful. So first step, we are gonna need to download our dependencies. So stb image. Okay, the next one, stb image resize, and this one is needed, as I said, to resize the train images. And the main reason we need to resize them is because the model will have a constant input size. So in the intuitive way, you'd think that the model size changes as the image changes, because my friend Johnny has a different phone, I have a different phone, so why wouldn't the AI model change to adapt to our different, cameras? But the truth is that the model has a constant size, and actually the images have to adapt to that size. That's how it usually works. So yeah, maybe it doesn't make that much sense, but no, it's not that important right now. It was just the fact that I couldn't find a simple data set. So I thought, either I do the resizing myself, or I guess it's pretty simple, and it's also, in my opinion, a bit fun to see how it's done. So why not? Like, you can just ignore the fact that we just a small part. So let's start as usual with the hello world file, right? So main printf hello world, and then a new line. All right, let's gcc it and run it. Okay, perfect. So for this one, I was thinking to use a makefile, and just because we have, let's see, we name it main main, why not? And we are gonna need lm, so math for stb image, right? So that's the reason. So stb image, right? To use this header on library, I mean, I've used it in the past, so maybe if you saw me using it, makes sense. I also have my own, the ds.h, which works in a similar way. So yeah, you define this thing, like the header library looks like a header, right? It makes sense, but it also contains the implementation of the functions. So in school, in uni, they say, oh, it's bad to have the implementation in the .h file. I mean, it is, because the .h file gets included in multiple files, so it's a bad idea to define it there. But doing it like this with stb image implementation actually makes sense. It's I don't know, it just makes dependencies easier. Like, you just download a single file and you have the dependencies, so it makes sense. Okay, the next one is resize. So for resize, we need this define, stb image resize, and for include stb image right, we need the right implementation. Okay, so let's see, because I was thinking to have some kind of I guess let's start with loading the dataset, right? So it's gonna be like a void load load image, let's say, and I want a construct pointer file name, and I want to output, I guess, a float, but we need the image size. So define image width 128 and define image height 128. The 128 numbers are pretty random. I have no um, I don't have that much of a reasoning for why 128, but it's just that. Okay, and the next thing is that we need a pointer to the output image. I want to implement it like this, with getting here a pointer to the image and change it, instead of returning the thing. I think it's nicer. Okay, so if we take a look in stb image.h, we can find an interesting function. It's gonna be something like stb load. I can search it from top. Load, right? So load, it reads an image from a file name. It also gives us the width and height and the number of channels, and it allocates the entire thing for us, so it's pretty cool. But I would like another one that loads the image as a float. So right, and I mean, it's basically the same thing, but the data type that's going to be used for the pixels is going to be floats. And I guess it makes sense. If you think about functions in math, they usually work with floats, so probably it makes more sense. So let's define a couple of things that we're gonna use. First of all, X, Y, and channels, right? And then we are gonna call to this function. So float data is gonna be pointer is equal to stbi load f file name. Here we pass the address of xy, which is I guess width and height. I can call them width, height, and channels. And the number of desired channels is gonna be 3. I don't think the images have alpha, so it's gonna be just RGB. Okay. Now if we try to printf, let's try to printf some numbers, but let's do it with a for loop. So for I is equal to 0, I is less than width times height times channels, right? I plus plus. Well, let's not forget printf, but we need to show float data I. So yeah, like the image is already flattened, as I said, right? So it's not gonna be, I mean, usually it's easier to consider the image just as an array of pixels. Well, that's even how I usually have the data structure for images. So yeah, okay, and let's do like make and main, right? I mean, we didn't call the function, so my bad. But I'm gonna do something like load image, and let's do data train, and then cat 0 JPEG. Oh, and for this thing, let's do null for now. So we can see the pixel values, and these are like pairs, RGB, right? So this is R, G, and B, and 3 of them form a pixel. But let's try to use stb image write. Let's write, so we read the image, let's write it. So write JPEG. So let's do like output.jpg, so we find it easier. It's gonna be width, height, yes, height. This is the channels, then we pass in the data, but it's interesting because data needs to be in char format. So if we run this thing now and we take a look at output, it's gonna look really weird, right? That's because here we have float, but this one expects the data to be in unsigned char format. So that's a bit sad, but let's allocate. I mean, we have to allocate some memory. It is what it is. Char pointer, some data is malloc with times light. But this one is just for. Oh, I shouldn't have deleted the for loop. 1 sec. Let me just steal it. Some data I, like this one is just sign char for the demo purposes. 255. Wait. Okay, and here we can do some data. So yeah, basically, if we multiply the float value with 255, we get the character, or I guess the, the colors are between 0 and 255, so why would you think it's different there? Okay, and now the image looks the same as the one from the data set. But again, we want the images to have this size, so let's try to use stb resize. Actually, let me just go to the header file itself and let's try to find the resize. A lot of comments, but the resize should be, so yeah, basically the resize, we can use this function because it works with floats, and we pass in the data, right, that we just loaded. Width and height is the width and height of the image, and then we have to pass in the result like container. We can also pass null if we want to make it allocate for us, but it's easier like this, since image is also output. And then we have to pass the size that we wish the image should be, and then the image type, so RGB. And yeah, if we now run this thing, right, we should be able to see the image, I guess. So it's in output. Yeah, and it should be resized to, the 128 by 128 image. So now, we just need to make a for loop. Int I is equal to 0, I should be less than count, plus plus. And in here we need to make a call to load image, basically. So it's going to be probably something like load image. We are going to do something here, and then we pass address train, or I guess it can just be train I, right? But here we need the file name. So file name, maybe like file name is gonna be 128 characters, right? And we can use sprintf, cool little function for the file name. So here is the file name, and the path is looking kind of like this. Right, so it's data train. This is the it's going to be the path, so I'm going to use it like this, then a slash, then it's going to be the label. We have a .d and that, and then JPEG. So this is how it looks like. So path, label, count. Yeah, and we can load the image. So instead of doing this thing like this, we can just replace it with, let's say, load dataset data train. Maybe I'll use dot, then cat. For the count, let's do 100, or I guess train count. And here is gonna be cat train. All right, so now we load multiple images at once. Let's do a for j is 0, j plus plus, j. we can just if you like examples slash, and this one needs to be done with sprintf. File name is going to be the same thing. And here we need, I think, J. Okay, so now we need the examples folder, and hopefully if we run this thing, we'll see in examples some images. And if we take a look at examples, weird, I would expect, maybe for some reason I loaded the same thing every time. Oh, yeah, who would have guessed? So let's retry this. And if we take a look at the images, all of them are resized properly. So, this is how the images should have looked like in the beginning, but it is what it is. Anyway, so yeah, now that we have the images, right, we can try to load more of them. So, but for that, let's also open htop. I was just curious how much memory it's gonna take to load like 1000 of them. So well, it was like 5 gigs, so not that much. But what about 10,000 images? I mean, I think it makes more sense like this because we're gonna see it. Right, so it's like 5 gigs. I think it should be like almost 10 or something. Right, so it still increases. It's not done yet. I mean, it takes a bit of time, not gonna lie, but it's 10,000 images, right? And it also needs to resize all of them. But yeah, you can see how much memory it takes, right? I mean, let's stop it. And what if we do here stbi image free data, right? What if we do a free there? Is it gonna still take that much memory, or is it gonna be better? So no, I mean, the reason why C is the better language, I guess, well, any language that has manual memory allocation and freeing. Although, Rust doesn't have manual, but it still happens like manually if you think about it. So yeah, like it doesn't even go over 4 gigabytes, right? So that's the problem with Python. Well, it went over, but I think it should be much better if we free the data. And we don't need to free this one because it's already on the stack, so we don't care about it. But yeah, like it should be much more efficient with the memory if you free this stuff, if you don't forget about it. So yeah, you just have to make sure you don't forget about freeing the memory that you don't use. I mean, in Python it does that automatically with garbage collection, but yeah, you don't know when it's gonna happen. But yeah, I mean, it should be much better. It's funny, we can see like 300 megabytes being allocated. Whatever. So let's just leave it be. Now, yeah, the bad thing is that we cannot really have like a notebook and load all the images and keep them loaded in memory. Like, we cannot do that. But at the same time, we'll see. We'll use like a really small amount of images, and when the time comes, we can increase it to the real number. So let's also have dog train, right? And let's load the data set for dog. And let's see. So we can just rerun the entire thing, and we should have dogs in the example folder. So we have dogs, right? Pretty cool. I mean, there were also some cats, but doesn't matter. Okay. So I guess now for the interesting part, which should be the feed forward of the model. Let's start with the simplest one. So the simplest uh, function that I guess talked about should be like it. I guess let's do it in the main, right? Let's remove all of this. We don't need it anymore. So it should be like it has a float W for the weights, and this one can be random, and it also has a bias. So these are the parameters, right? So the params of the model. And then we want to compute the output, which is going to be W times X plus B, right? And I guess let's comment this stuff out. And then for X, we can have like this is the input. So it can be like 1.2 float. And like this one is the simplest model, I guess, right? It has a single weight and a single bias. But in our example, we have quite a few more inputs, right? We have 128 multiplied with 128 multiplied with 3. So it's like, not sure. Let's try to compute how many. 128. It's almost 50,000 inputs, right? So we would need also 50,000 weights, one weight for each input. So I'm thinking what would be the best representation for that. Not sure if I want to declare them globally, although I might just do that. Like have here the, let's say, float but even calling it like layer, well, maybe we can do like weights, right? And it probably makes sense to have image weight times image height times 3 equal to 0, whatever. And if we want to add multiple layers, because we can also have that, we can do the same thing as we did for this thing, like have here a number. But what it's not gonna work for this is that maybe each layer has a different size. So probably will say weights 1, weights 2, and so on if we want to have multiple layers. But this should be the weights, right? And we also need the bias. And yeah, I mean the bias is gonna be only one number because it's applied to the output. But yeah, should be only one. Okay. So I guess the next thing would be to implement the dot product because that's what we are gonna need here, like a dot product for stuff. So let's do, usually dot product, it returns a single float. So it's gonna be dot product, and let's have float pointer weights and float pointer input. Although we can just say, x's, y's, and maybe you can have an integer for the size. So then float sum is equal to 0. And now we just have to iterate all of these. So sum, so this is how dot product is implemented, right? It just multiplies component with component and adds all of them together. Okay, so what this means, I guess, is that we can actually define the model now, right? At least the forward pass of our model. So not sure. I mean, let's write it here. So let's do float read forward, and yeah, as I said also in the presentation, is like float. It returns the probability of the image being a cat or a dog, right? So that's what it's gonna be. And for the input, we need to take in the x, like the image, and we'll have these things global, so we won't care about like having structures and stuff like that. We can just use these things globally, although I don't know, maybe a structure makes sense. I sure could use a structure, not necessarily a need for having this like this. I mean, yeah, sure, why not? So yeah, we can actually have a structure, let's say, and let's call it neural network. We don't need to initialize it, but yeah. So it's gonna need the input weights, right, to be of this specific size to match with our images. And this is why we needed to resize the images, because the inputs are gonna be only this size. We cannot change the input weights. It doesn't make sense. So let's call this like input because it's our input layer, and we can add more as we become more advanced. But for now, we can imagine that our neural network is gonna be just a single layer, and here we want to take in the neural network. I mean, we can just type defit like this. We can make it pointer, but not needed. Like maybe const, right? So it's not changing, but like that. And I would say for the forward, you usually need an input example. So let's call it X. Should it be maybe, I think it's enough to call it like pointer X, and we know the size of it is gonna be like this, like the only way. So let's implement forward based on what we know here, right? So, or I guess even from what we know in general, like it should be the dot product between the weights and X plus B. So it should be pretty easy how we apply these weights, right? So dot product, here we pass n's arrow weights input, here we pass the X, and the size is gonna be image weight times image height times 3. Maybe channels, it's define, let's have image channels instead of 3 just in case. There's also another one here, they think weird. Anyway, image channels. Well, I guess I mean, yeah, sure. I don't know if I would say here like const. Like I don't care about changing the pointers. It's just gonna be const. So, this thing is the y, or I guess maybe it's better to call it actually it's like y, and let's add the bias on top. All right, so then we just return this thing. So right now it's pretty simple, right? It's just dot product for our feed forward, but yeah, I mean that's enough for now, and we'll have to do the actual learning, but this is basically how inferences and stuff like that runs. So it's just multiplying the weights with the input. Okay, so now that we have our, let's say, model, why not, we can implement an evaluation function. So I guess let's load the dataset, right? Let's define neural network NN. Maybe having a function that initializes with random numbers, this thing would be a good idea. NN init. Let's call this one NN forward, right? Like in PyTorch. So NN init should take in neural network pointer NN, and here we just want to initialize these with random numbers. So let's try and do something like equal to 0, I goes to image, image channels, weights input of I is gonna be I think it's an stdlib. Wait, why did I call it? It should be void. And then nn bias input should also be like random. Yeah, I thought weird because we don't include stdlib, but whatever. So this one returns an integer between these two numbers, but I would like it to be between 0 and 1, honestly. Or actually between -1 and 1. So we could divide with randomx, I guess. This would give us a number between, well, let's do like float. Right, I don't remember which one needs to be float, so I'm just gonna, I think if you divide with a float, it's gonna be float. So now it's a number between 0 and 1, right? So if we subtract half, subtract half and multiply by 2 minus 0.5 f, this should be like a number between 0 and 1. I can even do like float rand 0, 1. Oh, let's just take this thing. Right, I think. Well, it's -1, 1, but actually let's rename it to rand 1, 1. Okay, whatever. So it's between -1 and 1. I think. So if I do here rand 1, 1, let me just comment this out. I mean, we would have to also, don't forget about s rand time null. Yeah, but I don't remember. This is in time.a. Yeah, I'm also gonna include stdlib because it's better to be explicit. Okay, so now it's like, hopefully it's gonna be between -1 and 1. That's all I have to say. So yeah, here we define the nn. So let's nn init to initialize our nn. And then we load the data sets for our train. But yeah, we'll probably want to also load it for the test. So let's do and then let's have like test count. right? And we can just say here test 1, test count. And we are more interested in the test data sets. Okay, so let's see if it loads it. Okay, loads it. And now let's try to compute the accuracy, for example. So let's do like total is equal to, probably test count times 2, but it's gonna be 0. And then we have the corrected predictions. But for now it's gonna be random, so we imagine that it should be close to 50%, but maybe not. Let's do a 4. It's less than test count. Right, so I guess what we can do, well, actually we'll also need to add another thing, but we'll see in a moment why we need to add that thing. Let's consider that if the probability is close to 0, then we have a dog, and if it's close to 1, then we have a cat, right? So that's what our neural network is gonna return. So if we do nn forward, right, we need to pass the nn. So nn, and let's say we do a cat test. For now, right? And maybe like I. So this is gonna be load prediction, and let's print f this this prediction. Let's just try to see what it's gonna show us. Interesting. Quite interesting, to be honest. I mean, yeah, I really wonder why it shows that. I mean, cat test should be, I was just thinking maybe it's gonna be zeros, so that's the reason. But like, we can also just printf some floats from our image. So image, oh yeah, for some reason it's all zeros. Pretty interesting. ls, oh, so damn it, I mean, obviously the test images are not labeled. So yeah, fine, because this was like a casual challenge. Okay. So we need to build our test from train. So whatever. Let's just use train for now. So now we should see like different probabilities we would expect but instead they are like random numbers. So, that's not that great. And the solution for that is to use an activation function, right? And the activation function should take any number and give us a number between 0 and 1. And one such function is sigmoid, which looks like this. I know it's pretty ugly, but I mean, actually, it's quite simple, but it would be really weird to think that it returns something like this. So yeah, let's try to use it. So let's define it somewhere like here. Sigmoid. It takes in a number and returns a number. And the idea is to just try and do 1.0 divided by plus x. It's from math.h. And here is minus x. But I guess I want xf for float. So I mean, it's pretty simple. Probably it's hard to find the intuition why it works. Like you'd have to, take some examples and see how you draw them on a graph. But if you can, trust me that it returns a number between 0 and 1 always, it's pretty cool. So that's why I was thinking to call this one Z, and then Y is gonna be sigmoid Z. And now we should actually see numbers between 0 and 1, hopefully, right? And there's also this thing about sigmoid that if you can see on how it looks, that if it's greater than, I don't know, 4 or minus 4, it is quite steep. So if the numbers are close to here, it's pretty uncertain. But if you go beyond like 4 or 5, it becomes like 100% or 0%. So yeah, that's another feature of the sigmoid. Right? The higher the number we get from here, the higher the confidence of the model is going to be. So yeah, so as I said, if like prediction is going to be higher than 0.5, let's say, we do correct plus plus because these are the cats, and then we do the same thing but for dog. And for dog we need smaller than 0.5, and let's do equal here. Wait, what? Okay, equal. And at the end, let's do a printf, and let's see the correct divided by total. But we should do float. Oh, and yeah, total is going to be 2 times test count. Although we don't even use test count anymore. Here's the trend. Why not? Okay, so let's see what the accuracy is with like randomly initialized, right? Whoa. No, that's pretty interesting. Oh, because I put them. Right. I mean, I would expect to see something like 50% or something close to that, because that's what the random does, right? So it's 44, right? So yeah, no, pretty much random. So I guess the goal for us would be to actually, train the model, meaning we need to find what weights are good for our dataset. That's all we have to do. And yeah, we'll have to see how we do that next time when we implement backpropagation and all of that stuff. So yeah, and yeah, actually we'll see how you do like calculus stuff in C basically. So probably it's not gonna be complicated as you imagine. Right now the model is not that great, but we can train it to make it better. I will show you how to do that in the next video, so don't forget to subscribe to not miss it. So far we have used only simple math concepts like addition and multiplications. Also minus and division, but that's another story. Sure, we have touched a bit also on vectors, so 1, 2, 3, and so on, and also vectors like this. Also a bit of dot product, so the formula for dot product is like x1, 1, just to give you the math for it. But you don't really have to be an algebra expert to understand what we discussed today. Like, this stuff is enough. Maybe the other thing that we also saw was the sigmoid function, so that's pretty useful to know. Although it's more important to know that it looks like this rather than what it does. You have to know that it's between 0 and 1. That's the only thing you need to know. And all of these other things, like the dot product, is more like syntactic sugar that we use on our functions to make them easier to read. Like, it's much like a dot product, a multiplication is much easier to read than this entire sum. So that's another thing. And I guess something that I would consider a bit overrated, I put like 4 exclamation point, is knowing the calculus. So the entire derivatives and the integrals. I mean, integrals, I don't even think you need integrals for machine learning, but who knows. Yeah, I don't think you need them, but whatever. I think they're a bit overrated, because you'll see why in the gradient descent and backpropagation videos. Sure, it's useful to know the formulas, but I think the intuition of why do we use them is more important. Like, why do we need the gradient? Like, what the fuck is the gradient and why do we need it? I think that's more important than knowing the formula. Like, if you understand why it's being used and what it represents in the real world, then it's more important than knowing formulas and all of that stuff. Because the formulas, you can find them online. It's extremely easy to find formulas. You can just use ChatGPT to generate you the formula, so pretty easy. So yeah, you don't really need to fully understand the derivatives and the advanced calculus to build a neural network. But they're gonna be used a bit when we train the model, but that's in the next one, so you'll have time to think about it. So yeah, don't worry if you are not a calculus expert. You can still learn a lot from this series. So yeah, don't forget to like the video if you want to learn more. And yeah, that's it for today, and I hope you enjoyed this video, and I'll see you in the next one.